Okay, now we're going to get into the nitty gritty of DNA replication. So I'm going to draw the double helix like this, like it is on your doc. We're kind of looking at it at a horizontal orientation. You could draw this vertically. It does not need to be horizontal, you understand, right? There's no rule about that or anything. And also, this is going to be a closed loop. I'm going to draw in a second, but I'm going to leave it like this for a minute. This is where it's really important for you to remember the anti-parallel nature of DNA, that there's a 5' end and a 3' end of each strand. So I'm going to label, there's no clue that tells me which is which right now. I'm just going to make up the label myself. I'm going to say that's the 5' end of this strand, which would make down here be the 3' end. And this is the 3' end here, which would make this the 5' end. Remember, DNA is anti-parallel. If you don't remember 5' and 3', remember this has to do with which direction the carbons in the deoxyribose sugar are pointing. The 5th carbon pointing this way, and the 3rd carbon where the phosphate's attached pointing this way. So it's just the directionality of the molecule, right? So when DNA replication occurs, we're going to have the enzyme, and all these enzymes are defined for you on the doc. So use the doc as a guide here, but you are going to have the enzyme helicase attach more or less here at what's called the replication fork, and it turns and it unzips. So the molecule is going to feed through it, and it helicases the unzipping molecule. I think of helicase, I think helicopter, spinning and unzipping. I also think about what do helicase and teenage boys have in common? This is really cringy. Sorry, they both want to unzip your jeans. Okay, so that was inappropriate. It's like one thing making an inappropriate joke with you guys in class. It's another thing like recording it to video. That just did not feel right. Okay, that's DNA helicase. Now, DNA polymerase is going to be the one that extends the molecules, adds new DNA nucleotides. Remember, we've been talking about RNA polymerase in transcription, right? RNA polymerase is what copies DNA into mRNA. Here, there's no RNA involved, although there is a little bit, but we're not actually replicating RNA or making mRNA. We are copying DNA. So DNA polymerase is our enzyme. There's a few different DNA polymerases, but you don't really have to distinguish between them. So if I were to come in here and add a new nucleotide there, and then another one here, and another one here, right? Think about this new molecule forming. This would be, if this is 3', this would be a 5' end, this would be a 3' end, right? So DNA replication is occurring this way. The weird thing about DNA polymerase, and RNA polymerase too for that matter, is these enzymes can only extend nucleic acids in the 5' to 3' direction. They cannot go in the 3' to 5' direction. So in other words, we can jump on here and zip on down this way, but we can't jump on here and zip on down at the same time, right? Because if I were to add nucleotides to this one here, right, like this is, if that's 5', this is 3', and this is a 3' to 5' direction right there, can't be done. The enzyme can't do it, right? That's the first thing to get. So we call this strand right here, this top one, this is the leading strand, right? I actually think you should, if you're going to draw this, label it over here, actually, because I'm going to use this space in a second. So leading strand, and this is the lagging strand. Lagging strand, okay? Now, the way you know the difference between them is on the leading strand, nucleotides are added continuously, right? If you imagine another nucleotide, another nucleotide, another nucleotide, and then helicase continuously unzipping it this way, the whole molecule moving through this way, we're just going to continue unzipping it, and this strand is just going to be the entire 3 billion letters. It's going to be continuously down the entire genome until we've replicated a new DNA molecule. That's the leading strand. Easy. There's nothing much to understand about it, right? The only detail I'm going to add for the leading strand is every time this starts, we do need to have an RNA primer first. So we are going to have, I'm going to label it above again. We are going to lay down an RNA primer to get things going. But other than that, the DNA is just going to be added by RNA polymerase. You don't need to explain why there needs to be an RNA primer, just there needs to be a little short segment of RNA added by RNA polymerase for DNA polymerase to really attach. That's just about DNA polymerase attaching. Once DNA polymerase, the enzyme, is attached, you can imagine it as like a big blob on the DNA like that. It's just going to continuously move down the leading strand and add nucleotides. Okay, so that's done, right? For the lagging strand, it's a little trickier. Remember, DNA polymerase can only add in the 5' to 3' direction. So that means that DNA polymerase is going to jump on here, right? Imagine this blob like here, and add nucleotides this way. Boom, boom, boom. In this direction, which is, if you think about this being 5', that makes this 3', that makes that 5', and that, it's like starting from the inside going outwards on the lagging strand. Now, if you think about it, I'm just going to erase this to pretend that DNA polymerase is there, right? So it jumped on here, right? It does need an RNA primer, so there has to be an RNA primer laid down first. It's a little bit tricky to remember that, right? But once the RNA primer is laid down, DNA polymerase is going to build out, but it can only build out to the end of the strand here. It's actually not the end of the strand, but it's going to build out this way, right? So it's only going to be a short piece. And then this is going to continue replicating, or I'm sorry, continue unzipping. In your mind, unzip more of this, right? I'll actually do it on the board, right? We're going to unzip more, right? And now that stuff is opened up. So how can they build again? They can't continue and go this way. They have to jump on here again and go back out. So RNA primer laid down, and then new DNA molecules added this way. And notice I'm going in a 5' to 3' direction, both times. Now notice what I have. What I have here are two new fragments. Right here, they are not connected, right? There's a space there, because they've been added non-continuously. They've been added in fragments because of the nature of how DNA polymerase has to work. So these two things are called Okazaki fragments, for the name of the researcher that discovered them. Okazaki fragments need to be attached together. You also have to replace the RNA primer with DNA, ultimately, or I should say eventually. But the way that these two fragments are going to be attached is with the enzyme DNA ligase. Ligase is going to attach the Okazaki fragments so we have a continuous strand. But the bottom line, just to sum up everything, and my molecule is looking very messy now, so look at the dock picture. I'm going to redraw it actually. To sum up everything, on the leading strand, DNA fragments are added continuously. On the lagging strand, they are added in fragments called Okazaki fragments. This is because DNA polymerase can only extend DNA in the 5' to 3' direction. Now, I want to remind you that when you see a drawing like this, and you've got your DNA here, this is actually a replication bubble. Here's the replication fork, like a fork in the road. And this is actually going to be a bubble like this. So when you zoom out, actually, you are realizing that DNA is being extended in both directions, actually, that there's a helicase here and there's a helicase here, right? So this would be like the point at which new DNA gets added. So here, boom, 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 boom. This is 5' to 3', right? By the way, remember, if I could pick this up right now and flip it around, and that would put the leading strand on the bottom. So it's not, this is an important point actually, it's not that the leading strand is on the top all the time, or in this case, the top left. You have to look at the directionality, right? This is a 3' end here. This is a 5' end down here, right? I just made a little 5' down here, right? So That's how I know that this is the leading strand. It's because this is a 5' to 3' direction, right? This strand could very well be on the bottom. You have to look at the orientation of the molecule, right? Here, again, what are we going to do on this strand? Well, remember, this is a 5' end here, and this is a 3' end. So that means that this would be, the new strand would be 5' here to 3' here. So we've got to go out that way, right? So here's our Okazaki fragments. So I'm going to jump on, build some DNA, wait for the double helix to unzip a little bit more, jump on again, build some more DNA, right? Going this way, right? That would be 2 Okazaki fragments. DNA ligase has to attach them together, make that phosphodiester bond. And then we start to build our 2 molecules. Now here, think about it this way. If this is 5', that means this is 5', this is 3', right? 3' end, 5' end. This is 3' end over here, 3' end to 5' end. So what is happening when you start to build this one? DNA polymerase is going to jump on after an RNA primer, of course. I'm excluding RNA primers from this drawing just for simplicity. So here, can I build this strand continuously like this in this direction? Yes, I can, because this is the 5' end and this is the 3' end. So here, this is the leading strand on this replication fork, right? And here is where I need the DNA polymerase to jump on here and build outwards and make Okazaki fragments. So there's one long Okazaki fragment, wait for it to unzip, 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 jump on at the fork again, build out that way. This is 5' end to 3' end. Notice that this is the same orientation, right? 3' to 5', 5' to 3', right? 5' to 3', 3' to 5'. Okay, this is tricky. I have one of my proudest achievements, you guys, honestly, is the cardboard Velcro strings I built in order to get hired at VHS. I did a demo lesson about DNA replication, and I built this molecule that allows you to replicate this as a model. And honestly, I feel like that's why they gave me the job at VS, because they liked my model so much. I wish I could show it to you and we could do it together as a class activity. I'm so lonely. Okay, bye.